Welcome everybody. My name is Maurits, and today I will present to you the paper AB-UPT, Scaling Neural CFD Surrogates for High-Fidelity Automotive Aerodynamics Simulations via Anchor Branch Universal Physics Transformers. This is joint work with the colleagues from ME, Benedikt, myself, Reinhard, Tobias, Reinhard, Matthias, and Johannes. And recently this work got accepted at TMLR, and we would like to present it now to you. So this is the outline, the brief outline of this talk. So first we will introduce the notion of problem scale in neural simulations to you. Then we introduce AB-UPT, which consists of a new multi-branched architecture, and we introduce a novel way of attention, which we call anchor attention. Then we will motivate our architecture or model paradigm with experimental results, and we finally will discuss some limitations and future directions and conclusions. So in this paper, we would like to address the question on how to define and harness scale in the context of automotive neural surrogates for CFD simulations. So for those of you who are in the field of AI, we all know the notion of scale in terms of model parameters that are scaled, the scale of data sets we deal with. But if you look to simulation data sets, and especially industry standard data sets like driver ML, the scale is more or less in the number of simulation mesh cells that you are using. So for example, driver ML consists of over 150 million simulation cells, and other data sets like AMET-ML is an order of magnitude smaller, but still consists of more than 20 million simulation cells. And if you look to data sets like ShapeNet with a small problem scale, they have a low number of simulation mesh cells, and also they model simple physics phenomena, while the large problem scale data sets have a high number of simulation mesh cells and model complex physics phenomena. So if you have the triangle scale, like data scale and the number of data points, model scale and the number of trained parameters, we will actually focus on the scale of the problem in terms of simulation mesh cells. And to address this problem, or to advance this field a bit, we introduced the Anchor Branch Universal Physics Transformer. So the contribution here is twofold. We first introduce a new multi-branch transformer architecture, which will I discuss first, and next we will introduce anchor attention, which is a new form of linear attention, which enable us to scale to mesh cells of hundreds of millions of simulation cells. So our multi-branch architecture consists of three branches, which all model their own modality or physics. And we first start with the surface branch. The surface branch the goal of the surface branch is to model the physics on the surface of the simulation mesh by taking queries of the surface, and there is self-attention within the branch and cross-attention to the volume branch to model the interaction between the surface and the volume mesh. We have the volume branch, which does the same, but then reversed. So it takes in the queries of the volume mesh, the volume simulation mesh, and it has self-attention to model the physics within the branch, within the volume, and also cross-attention to model the interaction between the surface and the volume. But what is new here is we introduce a third branch, the geometry branch, and this allows us to decouple the modeling of the geometry. We decouple it from the surface physics simulation and the volume physics simulation. And the goal of the geometry branch is to encode the geometry into a reduced small set of latent geometry tokens. And the surface branch and the volume branch are able to attend to this encoded geometry by using cross-attention and to retrieve the information from the geometry that is needed to model their physics. So this is in a very high detailed overview of how we implement it on the network architecture level. We will, for all the details, we refer to the paper, but we will go over it in high level, step by step, to give you a bit of an idea how this is modeled. So we first start with the encoder block, and the encoder block encodes geometry by using a supernode pooling layer and followed by a self-attention layer to map the geometry in a small reduced set of latent tokens. And there is cross-attention with the transformer layer between the geometry branch and the surface and volume branch for the surface and volume branch to retrieve the information it needs from the geometry. Next, we have a K or number of what we call physics blocks, and each physics block is an interleaved block of a self-attention layer and a cross-attention layer. So let's focus on the surface branch now, but the same logic holds for the volume branch. So first, we start with the self-attention layer, where only interaction within the surface branch is modeled by using self-attention, which is followed by a cross-attention layer, so that the surface branch can attend to the volume branch to model the interaction between the two branches. And this is repeated a number of times, a number of blocks, to model the physics in both branches. And finally, we end up with a few branch-specific decoder layers, which do not share parameters. So the parameters of the physics blocks are shared between the two branches to model the physics within each branch, within the surface branch, and within the physics branch to come to the final output prediction. So this is our new multi-branch architecture. This is basically our model. But our model, as you just have seen, relies heavily on the transformer architecture and therefore on the self-attention block, which has a quadratic compute complexity and memory complexity given the number of input points or input tokens. And if we want to scale to simulation size meshes like driver net with hundreds of millions of input points, this complexity will explode and will be infeasible to compute. So therefore, we introduce a new form of attention, which we call anchor attention, where we start with, let's say, n input points, input tokens. Let's take 100 million in this example, similar to driver ML. And from those n points, we take a very, very small subset of m anchors, which we call anchors, which then m is way, way smaller, like an order of magnitude smaller than n. And those anchors, which we usually sample at random, we use for the keys and the values of the model. And then all the other points are just used as queries. And this results in the fact that the self-attention computation has only a complexity of the number of queries times the number of anchors, which reduces the complexity from n squared, the number of queries, to n times n. And it scales linearly with the number of queries instead of quadratically, which just drastically reduces the number of the complexity we need for the attention computation. And this allows us to focus on problem scale, because now we're able to scale the problem to millions of query points that we need for these industry standard simulation meshes. And we apply this anchor attention in both the volume and simulation branch. Another nice benefit of this new formulation of attention is that the query points become independent of each other. There's no self-attention anymore between the query points, which turns our model into a neural field. So we have the neural field property, which is interesting for a few other things we like to compute, and which we will discuss later. So if we compare the properties of our AB-UPT to numeric solvers, but also other neural CFD solvers, we see that AB-UPT is more or less favorable in terms of accuracy, but also in the number of context tokens we can use, the speed for training and testing, the fact that we are able to decouple the geometry, and that we are also a neural field decoder, or we have the neural field decoding property by design of the anchor attention. So now we would like to motivate this model architecture with some experimental results. So we first of all tested AB-UPT on the standard benchmark of the academic standard benchmarks dataset ShapeNet, AMET-ML, and DriverML. We compute the pressure, the surface pressure, the volume velocity, and the volume vorticity. And we see that our model outperforms all the baseline neural surrogate models with sufficient margins. And especially if you look to TransSolver, we are quite a margin ahead of the TransSolver models on all metrics. And we are also better or comparable than a full transformer. If we are able, and why is this interesting, is because the transformer has full self-attention between all the volume points and all the surface points, which is super computational expensive to compute. But still, our multi-branch architecture is better than that, which is motivation of using this branched architecture, which is way more efficient, but also is way is able to outperform like a full attention model, which basically has all the context information available if it's needed. If we look to like integrated metrics like lift coefficient and drag coefficient, for which you need to do an integration over the full surface mesh, which can contain tens of millions of points, for example, drive ML, which we are able to do with like anchor attention, we can see that our model has very high prediction quality or very high correlation between the predicted lift coefficient and the ground truth lift coefficient as provided by the original simulation. And we see the same for the drag coefficient, which is also an integrated metric. And another thing which is interesting is from a scaling perspective, or scaling in terms of how we train it. What you see here on the top is the train loss for Transsolver, Transformer, and AB-UPT, given a number of surface and volume points that we use during training. And basically what you see is the more points we use during training, the lower the train metric, the train mean squared error becomes. But you also see that if we go slowly to 30K points, this, it already starts to saturate a bit. So the train loss does not become lower and lower all the time. But what we see on the lower plot is that the test metric actually goes up at some moment. So it starts to overfit. So even though we have simulation meshes for AMD-ML that contain millions of mesh cells, we actually don't need that many cells during training to get the optimal performances, because we start to overfit already very quickly. And for drive ML, we see not similar, but we also see that this metric starts to saturate. That does mean that for training, you don't need that many mesh cells to get the optimal performances, as we just see. But due to the design of anchor attention, we are still able to do inference with way, way more cells than we actually need for training. So we are able to do the problem scale inference by using the anchor attention. Then another property that we would like to discuss is that because of this geometry branch, which decouples the geometry encoding from the surface branch and the volume branch, we are able to use different points or different point clouds for geometry encoding and for the anchor encoding than the ones provided by the simulation mesh. So if we use a simulation mesh for both the geometry branch, the anchors, and the query points, we get certain number of performances. This is on AMD and driver ML. But if we only use the geometry mesh, which is way, way cheaper to obtain for both the anchors and the geometry, we still got quite decent performances. So for inference, you don't need these expensive simulation meshes to generate these expensive simulation meshes, to still get decent performances using our decoupled multi-branch architecture. Then the final thing what we would like to discuss is the physics consistency that we can model by using this neural field decoder property. So because of the reason that those query points are independent of each other, because they only have cross attention, we can actually add hard constraints to the model to make the predictions, for example, the vorticity predictions, physics consistent by making them divergence-free. So if you just train a naive AB-UPT and you you measure the divergence of the vorticity, you actually don't get zero, which should it be by design. But if we fine-tune a model by using this hard constraint, which we're able to model by using our neural field property, we barely have any performance loss while having the divergence-free property of a divergence of zero of the vorticity for both data sets, which is a very interesting property from a physics modeling point of view. So although this is all great, we are not there yet. So there are some limitations in future work. So in this case, on the data sets we tested mainly for AMD-ML and driver ML, we were able to have very good consistent performance with a very small number of anchor tokens, like 60,000, 16,000, 32,000 was enough. But for more complex geometries, more complex phenomena, it's very likely that you need more anchor points to properly model the physics. And at some moment, the quadratic complexity of the self-attention between the anchor tokens can still become a bottleneck. So we have to address that at some moment if the simulations becomes too complex. For now, we only focus on automotive CFD. We would love to extend this to more diverse set of engineering simulation problems, of course. And what is the data sets we evaluate on, like AMET-ML and DriverML, are a very high fidelity data sets, but also very expensive to obtain, which results in the fact that the variety of shapes and models of cars that we have in this data set is not that high. So we still don't know, we still have to explore how well our model works on a very data sets with way more variety of problems that we encounter. So to conclude, we wanted to address the question of how to define and harness scale in the context of automotive neural surrogates, surrogates for CFD simulations. And to do this, we introduced AB-UPT, a state-of-the-art neural surrogate model for automotive CFD simulations. We introduced a new multi-branch neural operator architecture, and also anchor attention, sublinear form of attention to scale to millions of simulation queries. Our design is mesh independent and allows for these divergence-free vorticity predictions to make the model physics consistent. And we investigated the notion of problem scale, where we scaled it to industry standard simulation meshes. So thanks for your attention, and are there any questions?